So we're in the middle of trying to understand loop diagrams and to work with them. And to do that, we've constructed a way of temporarily making loop integrals finite and various methods and tricks to help us then calculate in that method, in dimensional regularization. And it's described quite extensively in the lecture notes that you have, so you can certainly read up on that. And it should prepare you well for maybe also future field theory courses. And so basically what we've seen is divergences occur. That's a fact of life if you work with loop diagrams. So how to handle UV divergences. In the context of a theory. A given theory. And that brings us to the topic of renormalization. Renormalization is a way of consistently removing these divergences after they've been regularized. So regularization comes before renormalization. Occasionally you see still text where the two are confused. First you make the divergences temporarily finite, you make them would-be divergences, then you work with them through renormalization. After that you can remove the regulator. So here's how it goes, and we'll do it a bit schematically. So we'll consider QED first, but occasionally I will switch just to even a simpler theory. I will not do it explicitly for QCD, that's just more complication. I will just want to illustrate the concepts. So let's consider QED, which means that we write down the Lagrangian, minus a quarter. I'm going to write it now a bit more explicit, a nu a 0 minus d nu a mu, 0 squared. I do write, just for completeness here, a gauge fixing term, but I won't address it much. Minus psi bar 0 d slash plus m0 psi 0 plus I e0 a mu 0 psi bar 0 gamma mu psi 0. So that's the QED Lagrangian, where I have made a little label 0 on all the fields and the parameters of the theory. So the fields are A and psi, and the parameters are m and e0. I should also do it for the gauge fixing parameter, but that's a technicality that we can skip. So I won't treat this very much. But here we have the QED Lagrangian, and you've always thought, well, if this is m, that must mean the electron mass, and if it's e, that must mean it's the electron charge. But already we've seen in the diagrammatic analysis of charge conservation that is not always the case. So we'll keep that freedom, that it doesn't have to mean that, in mind. You also remember that if you derive Feynman rules from this, the quadratic terms become propagators. That is, this and this define the photon propagator. This will define the fermion propagator, and this is the interaction. Now, you can in some sense think of this bit as the inverse propagator. Remember, propagators, you take the kinetic part and take the inverse. Therefore, this is just the inverse propagator. And at the same time, you can think, if you write this in momentum space, this will be the inverse photon propagator. Propagators do have higher order corrections. Higher order corrections. For example, the photon, which we always write like this, the inverse photon or the photon propagator, we could imagine adding this diagram, where the photon has here E plus E minus loop inside. So let's look at this diagram. And momentum here goes k, here goes q plus k, and here q goes back. So it's very much like the one loop diagram we drew earlier. I just want to write down the formal expression for this within working it out in detail. In fact, you could even do it using the rules that we've learned this morning. So this thing, this self-energy, that's what it's often called. Actually, for this one, the photons and traditionally called the vacuum polarization diagram, which I'll give a more meaning to later. So let's call this thing pi mu nu. It has two indices, depends on k. And the Feynman rules, I just write down the expression you get from using the Feynman rules, but then won't compute it any further. 2 pi to the fourth. And I'll write it even in 4 dimensions, which I should really do differently. Gamma nu 1 over I q slash plus m. Gamma mu 1 over I p slash plus q k slash plus q slash plus m bracket close. So it's just going around the loop. You start, for example, here with gamma nu, go against the stream here. That's then the 1 over I q slash plus m propagator. Then we end up at gamma mu here, and then we go still against the stream to back to gamma nu. So that's this propagator, k slash plus q slash plus m. Right. So this is how you set it up. This you can convert, of course, to by multiplying upstairs and downstairs with minus I q slash plus m, and then you get the normal form. Right. So this, for example, I can write as minus I q slash plus m divided by q squared plus m squared. I'll just leave it for the moment in this form. One thing you can recognize from this is to see what is this a divergent diagram? Okay, that is correct. How divergent is it? How bad is it? That's quadratic divergence. But I have 4 integrals upstairs, only 2 q's down, so that's quadratic divergence. And possibly also less. The worst is quadratic. There may also be linear and logarithmic divergences. In fact, this one has some extra structure. This one you can actually write as k mu minus k squared eta mu nu times pi of k squared, just by arguments of gauge invariance. So this I'm just telling you, I did not explain this. But this argument shows that actually the divergence is logarithmic, because 2 momenta are extracted by arguments I didn't tell you, leaving only this thing, and that is then logarithmic divergence. So it's still divergent, but it's just actually logarithmic. So we have here a correction to the QED propagator that is divergent. There's also, for the electron propagator, we have this plus self-energy. So I don't even write an expression down. How divergence is this? Not quadratic. Linear, yeah. There's 1 power of method suppression from the fermion propagator, 2 powers of suppression from the boson propagator. That still leaves only 1. And also the vertex has, of course, the basic vertex plus, and then, for example, you have this diagram. Is that divergent? It's logarithmic. Okay, could there be divergences that we didn't have before? Could we have a divergent 4-photon interaction? Yeah, but it actually isn't, just by symmetry. So this is actually finite. If I make a 5.1, it's for sure finite. The more external lines, it's always finite then. So the only divergent diagrams really at one loop are for the photon propagator, the electron propagator, and the vertex. In fact, 3 elements which already occur at lowest order in the Lagrangian. There was no divergence of something what wasn't there. Right? There was no 4-photon interaction, and indeed there was no, at one loop there was no divergent 4-photon interaction. There is a finite 4-photon interaction at one loop. But that's fine, that just comes out. So the question is, how can we deal with it? Because if we can't deal with this, QED is a theory that has no predictive power. You have a finite number and then you add a correction which is infinite. That is not good for the quality of your predictions. So a key observation for renormalization is that M and E in Lagrangian have no physical meaning beyond 3 level. It's just parameters that have a certain suggestive name, but they're not necessarily the actual physically defined electron mass and charge. In particular, m-phys, the physical mass of the electron, 0.511 MeV over c squared, is not equal to m. In fact, this m and e can be infinite, which is what we will see. So, how does it work to actually renormalize? Well, so in dimensional regularization, we have, and I'll just give you the result, for this pi mu k is k squared eta mu minus k nu times e squared c over pi 1 over epsilon plus a half gamma e minus a half log 4 pi plus pi f. So I've written the bit schematically. So when you do the loop integral for pi mu, you get this structure in front. Here's the UV divergence. There was some number c here in front, which I just keep a bit abstract now. It doesn't matter what the details are. And there's finite terms. I kept also this gamma e and log 4 pi together with the 1 over epsilon. I will always do that. So okay, that's it. That's what you get for that one loop diagram. For sigma of p, and sigma of p is this. It's a traditional name. All books use the same notation here for this, and this is called lambda of p prime and p. So the self-energy of p has 2 bits that can be written as m times a plus I p slash b. And if you do that loop calculation there, you find that a is, oh, sorry, meant here is c sub pi. C, you give it the index pi to refer to the symbol. And then this one will be e squared c sub a 1 over epsilon plus a half gamma e minus a half log 4 pi plus some finite terms, and b, and we'll have e squared cb times this thing plus the finite terms in b. No, yeah, right. And finally, for lambda mu of p prime and p, I get E squared C sub lambda, and then again 1 over epsilon blah 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 plus lambda f. So here are the results, at least schematically, for all 3 loop intervals. And given this morning, you have some idea how you could get that. I mean, you have to combine denominators with finite parameters, do these intervals, do the finite parameter intervals in the end. And the examples are actually in your text. They're not very simple calculations, but they're doable. They're doable in a first year extended field theory course. So, but the result is that all of these divergence is explicit here, and these factors, I've kept the prefactors a bit arbitrary. In fact, you can be precisely defined. I just don't want to clutter the notation too much. Plus, of course, finite terms. But those are not the worry. The worry are the infinite terms. So, this is what you get. Now, how do you handle these? The problems are here. How do you handle them? So, now comes the big trick. I'd like to keep this Lagrangian on the board, so I'll just use it. Make sure I don't erase. So the question is how to handle these divergences. The 1 over epsilons. And the answer is renormalize the fields, coupling, and mass. Everything that can be renormalized should be renormalized. So that means that what I wrote as this field, A0 up there, I will write with a new normalization constant in front times a new field without the 0 index. And the new renormalization constant I call the square root of some factor ZA. The square root is a bit convention. Don't worry about it for the moment. For the psi field, similar, but now with a renormalization constant Z psi, actually, in fact, the square root of that. Sorry, there's no mu index here. That's for the fields. And for the electric charge, E0, I write as ZE, no square root now. And for M, 0 is up, is ZM. So clearly a new normalization constant. I'll already be thinking of these Z's. These are not some kind of weird functions. These are series in the coupling. There'll be one. All the Z's will have, keep that in mind a little bit already. I'll return to it numerous times. All the Z's will be like 1 plus E squared times something plus E to the 4th times something, etc. That also defines what the square root of Z is. You just put a square root over it and do Taylor expansions. But that's the structure of these Z's. Okay. So what we have to do is we could substitute this in there. Right, so what you get here, we can just do it, you can follow along. Let's look at the first term. I substitute for A0 my renormalized field. I get exactly this term back without the 0, with the factor ZA in front. And no square, that's why I have the square root, because there's a square there. So I get ZA in front. I will get something similar here. Here, well, let me just do it. So we get minus a quarter ZA d mu a nu minus d mu a mu squared. We also get here minus a half ZA lambda squared d dot a squared. And then here, I get minus z psi, psi bar d slash psi, minus z psi zm, m psi bar psi. Right, that's because this gets a z factor and these two as well. And the final term is plus, well, we get there, ze square root of za, and then z psi times e psi bar a slash psi. Okay. Nothing too spectacular so far. We just substituted this, and the real trick really comes now. And it's a bit of a, it's so trivial, it's a bit hard to appreciate. Here's the big equation that explains it all. I can write zi, any of these z's, as 1 plus zi minus 1. That's simple enough. Right. So, and that's what I use. So I can write now the Lagrangian, LQED, as so minus a quarter d mu a nu minus d nu a mu squared, etc. All terms I had here, these terms now without 0. This is if for all the z's I take the 1, then all that does is it takes a 0. But I get more terms now. I get plus za minus 1 times d mu a nu minus d nu a mu squared plus minus a quarter plus minus z psi minus 1 psi bar d slash psi, etc. I get all the z minus 1 terms. So we get the original QED Lagrangian in terms of renormalized fields, and I have a bunch of extra terms. I get those because I renormalized the fields. So if I would start computing these loop diagrams again, well, you erased them now, the pi, sigma, and lambda, I would do it with this part of the Lagrangian. This gives me the usual Feynman rules. Well, I get the now computed with renormalized fields, but for your integrals it makes no difference. The same Feynman rules, same loop diagrams, same intervals to do. If I compute these loop integrals with this part of the Lagrangian, I get the same result, the one of epsilon and stuff. But now, if I would write za equal to 1 minus c pi e squared 1 over epsilon plus a half gamma e minus a half log 4 pi. So then I get an extra contribution. So za minus 1, it's just this bit. So from this I get the loop integral, I get a divergence, and now from this term I get a second divergence, just because I defined it that way. That's of course a very it seems like a triviality. Well, I can cancel anything that way, right? And it certainly seems like that. So I just define ZA to have minus this divergence. So then I get that for this particular diagram, I have this original contribution that comes from this part of the Lagrangian, plus a new term that comes from this part of the Lagrangian. But this is only two fields in it, there's no loop, and the coefficient is, the infinite coefficient is just in front. So I usually draw it in this way. It's called a counter term. These are called counterterms. And the name comes from the fact I define these ZAs such that they cancel the 1 over epsilons that this part of the quantity produced. So I get an extra contribution at order e squared. You see it's order e squared. This one gave me the loop. The counter term now gives me a new contribution that precisely cancels them because I chose the two. And same for, I can choose Z psi to cancel the sigma divergence. I can choose ZE and ZM also to cancel these divergences. That's so far how far we are. Those are the logical steps. You see maybe how it works. You can envision how it works, but you may well doubt what's so special about that. I can choose, if I just always add a constant whose problematic term is minus the problem, I can cancel anything. Now the magic of renormalization is I'm sorry, I didn't quite understand.
For JJ terms, we can the first term.
This one?
Yeah, is a identity term, and you can find the overgetter from there.
Yeah.
Yeah, and for the Z A term, yeah, and can use that as a perturbation.
Yeah, we choose it as interaction. Next,
and we can form a Feynman loop from there.
Yeah, it leads to new vertices with these crosses, to counter terms. Yeah, yeah. So propagators and vertices are still divided here. These we indicate with crosses as new contributions. So what is the magic of renormalization? I've found here 3 problematic diagrams for QED, self-energies of the propagators and the correction to the vertex, and define the counter terms to cancel those. But there are other diagrams. There will be other situations if you have, for example, scattering, like this, or you have you also have such a diagram. There's many processes you can think of with one loop corrections that have UV divergences in them. Not just these 3 diagrams I analyzed. The statement now is that also these will have UV divergences, but if you just use these Feynman rules, those will cancel too. So by this fixing these ZAs for once and for all in these 3 simple examples, it will fix the one loop UV divergences in any other process. Whatever you do with QED to one loop, the UV divergences will be cancelled by these exact same counter terms. That's really the strength. You don't have to keep on fixing the problem. You just fix it once, but then it works for everything. Okay, I think that's what really should be impressive about renormalization. If you work really hard and compute also the 2 loop terms, the e to the 4th terms, same thing. You will find that whatever you do at 2 loops, these z factors will fix it all. And the same z factors. It's not that you need new z factors at every order. It's just these few 4 or 5 z factors. All you need to do is compute the next term in them, but you don't need a new one. If you go to 114 loops, you never need a new z factor. You can prove that. So it's still pretty powerful, actually, that you can, just by this simple renormalization, which then leads to these counter terms. If you then construct these counter terms in a few simple cases, they will fix your problems for everything. That's really not particularly precisely phrased, but you get the idea. So that holds true for a renormalizable theory. For non-renormalizable theories, that is not always the case. Gravity, for example, that will not happen. At 2 loops, you will need new interactions, etc. But for QED, which is a renormalizable theory, just a few z factors will do it.
The proof is by computing the terms and then showing that you don't need additional terms, or by on general arguments you can show that.
You can use very general argument. You can use induction. There's some these proofs you can actually give. There are in field theory books. You can show that you can, given you work up to order n, you can then see what the next order is and that it fits in either photons of energy or electrons of energy or the vertex or mass coupling.
Sir, diagrammatic
Yeah, well, that is a diagrammatic proof. You have to use word identities to show that, and those use diagrams. But what you don't do is you compute a loop, 114 loop diagram, and see what it is. That's not what you do. No one knows how to do that.
So, does it depend on gauge?
Sorry?
Does it depend on gauge, this procedure?
No, the principle does not depend on the gauge. The precise coefficients may depend on the gauge. So the self-energy, these lambda f and bf have some lambda dependence in it, and you have to take that into account a little bit. But the principle stays. In fact, not all diseases are independent. You can even show that I think this ZE and Z psi are each other's inverse, so their product is 1. So there are some identities between them. For QCD, the same happens, except it's a few more Z factors, but the same principle. And that was shown by my colleagues at Hoofd and Veldman. Well, long before I was active in this building work, really. In fact, this was the main thing about non-abelian gauge theory. That people thought, oh, beautiful theory, but we can't prove that it's renormalizable, that you have this property. It was too complicated to analyze this with the techniques then. QED was known for a long time, that was fine, but that really prevented people from taking non-abelian gauge theory seriously. And when they, using these diagrammatic techniques that they invented largely, could show this, that also QCD is renormalizable, then suddenly people took the theory very seriously. And in fact, it's the basis of the standard model. Okay, let me continue the discussion a bit. So at least I think it's important that you've understood the principle. The details are, of course, always a bit challenging when you really work it out, but the principle is important that you understand. That you fix these Z factors and that they will be there for the history books. In fact, of course, they are in field theory books, and they will fix it in any problem, in any process. So these counter-term contributions that follow from having renormalized the fields and the couplings. Counter-term contributions indeed take graphically the form of vertices. So you have already drew this one. It's a 2-point vertex in some sense. I always told you quadratic terms are for propagators, well, except for counter terms. So here you would, it's a 2-point interaction, but because it's a counter term, you count it as a 2-point vertex. A bit unusual, but that's what you typically do. And this is proportional to ZA minus 1. And this is proportional to 1 over epsilon. Right. At least at lowest order times E squared. You also have the correction to the fermion propagator. That would be Z psi minus 1. And it's also proportional to 1 over epsilon and E squared with some other coefficient. And you have, of course, the correction to the vertex Z E minus 1. At least that's part of the correction. The Z psi and ZA also come in, also proportional to 1 over epsilon E squared. Now it is perhaps also a bit intuitively not surprising that you get this structure if you have loop integrals like this. These are the cause of the whole story. Their divergences led to this procedure. The fact that you can cancel them by point-like interactions is not so surprising, because if the UV regime, when these momenta are very, very large, that means that the distances are very, very small. So it's that the very large momentum loop region leads to very short distances. Right? Large momenta are short distances. So it's almost like a local interaction that you're dealing with. at this point and this point are becoming very close. And same thing is, so these are local counter terms. And that's not so surprising because we're dealing with UV divergences. Also gives you a hint of why, if we're dealing with infrared divergences, if you have zero momentum photons, that will be a different story. Okay, so what I'd like to do next is focus a bit on one of these ZAs and one of these renormalizations, in particular on this one. Let me do that here. So now we're dealing with the topic of the beta function and also somewhat less extensively, but it's important to treat anomalous dimensions. These things are a byproduct of the whole renormalization procedure. In fact, you might think, well, all I want really from this renormalization procedure cancels my biggest problem, which is the one of epsilons. But by doing so, you get some benefits. You get the behavior of the theory on the scale changes, and this is what this is about. So renormalization has some powerful consequences. Renormalization, I'll abbreviate this way, has powerful consequences. So let's look at coupling renormalization in detail. And this is a little bit of a calculation that is not long, but it's good to keep track. So we have E0, that was the bare coupling, is E renormalized. So here I indicated the renormalized fields just by having not a zero on it. Now I make it a bit more explicit to have an extra R label for renormalized times of mu. Then we have the mu in the minus epsilon over 2. And this ZE, which is, as we know now, a function of 1 over epsilon and ER of mu, the renormalized coupling. So the right-hand side, we only have renormalized quantities, but also one of epsilons in the Z factor. Why was this here again? That's right. We had seen in the n dimensions there is a dimension to E, so this is dimensionless. So from this condition, we now may derive a consistency condition. So given this, let's act with mu d mu. This is a very often occurring situation in particle physics. You have a quantity which you can factorize as a product of other quantities, here ER and ZE, such that each of those factors contains a parameter, mu. There's mu here dependence, and here there's mu dependence there. But the product does not, because the product is the bare coupling that doesn't have any mu. So that itself is a very powerful condition to derive relations between the renormalized coupling and what sits inside Z. And let's see what that means. So I act with mu to d mu. I could have acted with d d mu as well, but it's more convenient to add another mu there. So what do we get? Well, on the left-hand side, I get 0. There is no mu dependence in the bare coupling. On the right-hand side, I get, let me first act on this mu factor, and then I get minus epsilon over 2, mu in the minus epsilon over 2, ER. I will not always indicate the mu dependence of ER, it's there, times ZE, plus, and now I act with d d mu on the E times Z combination, I get then minus epsilon over 2. And now I'm going to act with mu dd mu on the combination E times Z. Right? But the mu dependence in that combination only sits inside the ER. So if we use the chain rule, I can write this as mu dd mu of ER of mu, and then take the derivative with respect to ER of the combination ERZE. Right? So now we have an equation for the mu dependence of the renormalized coupling. We'll have to see what it is, but at least we have an equation. It may be completely useless, but we have something. And this only is relevant if we have done a loop integral, because if ZE is 1 because we didn't have a loop calculation, we don't need to renormalize, then this is a bit of a trivial calculation. We need to have done the one loop or beyond. But one loop is already instructive enough. So I can certainly see I can already cancel the mu to the minus epsilon over 2. And continue. By the way, this object, the mu to the mu derivative on the running on the mu-dependent renormalized coupling, this is called the beta function, which is a function of ER of mu. And that's what we want to solve for. So here we go. Beta is equal to epsilon over 2 ERZE divided by DER of ERZE. And I use the fact that ZE, I'll now write it exactly, is 1 minus ER squared mu over 12 pi squared 1 over epsilon plus a half gamma E minus a half log 4 pi plus order ER to the fourth that we haven't done. So this is not a difficult calculation. It's very explicit what you should do. Let's maybe make one or two explicit. So this is epsilon over 2, and then here we have ER minus ER cubed over 12 pi squared 1 over epsilon, etc. divided by 1 minus ER squared over 4 pi squared 1 over epsilon, etc. Now I expand this upstairs. I get then epsilon over 2 ER minus 1 over epsilon ER cubed over 12 pi squared. I'm being quite explicit now. Cubed over 4 pi squared plus finite. And this is epsilon over 2 ER plus E cubed over 12 pi squared. Notice that this now occurs finite. This epsilon cancels out 1 over epsilon. And I get a finite term. So we can also drop this. This is a high power of epsilon. We go back to 4 dimensions. And then we have, so in D is 4, in N is 4, mu dd mu of ER of mu is, by definition, the beta function of the running of the renormalized coupling of QED, and that is 1 over 12 pi squared ER cubed of mu. And there will be, if I calculate hard enough, e to the 5th, e to the 7th, etc. terms, but this is the leading term. So this is the beta function. It's a very explicit equation. Derivative is equal to this. It's a, you can think of it as an equation to solve, and we will. So this is the beta function equation or the running coupling equation. It's known for various forms. So already from the form itself, you can tell if someone gives me, it's a first order differential equation. So if I give it one initial condition, I can from there compute what E at some scale mu 0. Then if I solve this equation, I can then compute it for any other mu. That's what a differential equation does. Sorry? That will come later. I will explain that. Yeah. That will well tomorrow. Yeah. But it will have indeed precisely that physical interpretation. So well, given we have until 10 past, more or less. Yeah. Let me then continue actually with this. I was going to briefly do anomalous dimensions, but I'll do that tomorrow then. I'll stick with this. So we have this equation. Let's see what it means and what it leads to. Now, another key feature of this result is that the right-hand side is positive. Right, 1 over 12 pi, it's a positive sign. So a sketch of the equation will be, if I have here ER of mu as a function of mu, suppose here at some mu 0, I know what it is. Afterwards it will grow. And because it's a positive right-hand side. But we can actually be more precise than that. Let's solve this. I'll do it in a few big steps, and if you wish this afternoon, you can follow it. So we have here this equation, right? We have mu der d mu is 1/12 pi squared ER cubed. Now how to solve this? This is how it goes. So I bring all ER's to the left and mu's to the right, so I can write this as DER over ER cubed is equal to d mu over mu with a 1/12 pi squared. And now I integrate this from some scale mu 0, some initial scale mu 0, to a final scale mu, and then we call this then mu prime as an integration variable. And here I will integrate from some initial state I to the final renormalized coupling and put a prime there for the integration variable. Well, these integrals you can do, right? This is not too hard. So, and then what you do is you do the integrals, you bring the initial one to the right and this one to the left, and the solution is that ER squared of mu is equal to EI squared divided by 1 minus EI squared log mu over mu 0, 1 over 6 pi squared. You also see that makes, so if I make now, say, mu a little larger than mu 0, then this is a small number, and it's certainly much smaller than 1. If I now make mu a bit larger, I subtract more and more from this, so I divide by a smaller number, so the coupling rises. So this form is indeed reflects this behavior. If I divide by 4 pi everywhere, I can make this the running QED coupling constant, and that would be the one, say, at low energy, 1/137. And here, if I account for the 4 pi, I get that 2. So you see how the electromagnetic fine structure constant runs as a function of the scale mu. For example, at the E plus E minus collider at CERN, at the LEP2, LEP1, when they collided to make the so-called Z boson of 90 GeV there, the fine structure constant is 1/128, bigger than 1/137. Also worthwhile is another thing that the solution has, is that if you make mu large enough, then you're going to cancel the 1. So at some point, you really will hit a pole. And this is called the Landau pole. Where your renormalized coupling is infinite. Not so much from having UV divergence in it, but just because the running coupling hits some kind of extreme situation. It's a bit of a different divergence. It's where just this becomes infinite from this formula, not because of some loop interval. Of course, at this stage, you're in very dangerous territory. You shouldn't do perturbation theory anymore. If your coupling is infinite, better not use it for perturbative calculations. Also, this Landau pole in QED is a 10 to the few hundred or so GeV, way beyond what we ever can reach, even beyond the Planck scale. So it's in practice quite irrelevant. But in other theories, Landau pole is more relevant. But at least it's nice to see it here appear. Now, I maybe want to end with this thing on the story of QCD. So, we've seen this all follow from renormalization and one loop calculations. We drive quite a bit of extra information besides just cancelling divergences. We see that as a result of renormalization, we can introduce an arbitrary scale mu, and we can even calculate how that renormalized coupling depends on the scale mu. Tomorrow I will discuss a bit how you should think about the scale mu. So diagrams responsible in QED were, I've drawn them a number of times. So we had, for the vertex, this one. But in fact, I was a bit to put this other diagrams too at one loop that contribute to one loop corrections to this vertex. And these are the self-energy on this line, the self-energy on this line, and even the self-energy of the photon there. So these are all the one loop diagrams that contribute to the renormalization of that coupling. Now in QCD, and we've seen that all of this leads to this 1/12 pi squared. QCD, we have, very similar diagrams. We have this one. We have gluon self-corrections on this. We have this. We also have a fermion self-energy there. But now we have also more diagrams. We have extra terms there. We have a gluon self-energy there. We even have a ghost loop. There's one more diagram of that type that is perhaps it's often easily forgotten. In fact, it's 0, but you should write it down. The 4-point interaction. But there's also this one. I think these are all the ones that we have. So a number of other ones. The question is, if you compute all of these, define the z factors, compute for the QCD coupling the beta function, what do you get? So we had that for QED, beta is e cubed over 12 pi squared for QCD, we have beta is minus g cubed over 16 pi squared, 11 minus 2/3 times the number of fermions. Where number of fermions is the number of fermion types that can go around in this loop. So let me actually focus here on the second term. That gives a positive contribution, just like QED did. So in QED, actually, the divergences among these three terms cancel, and only this one remains. So that is then responsible for this positive term. And indeed, the fermion self-energies do contribute, again, a positive number. But we now have gluons, and they flip the sign. So they lead to this 11. And that is a negative number. This is the number of flavors that can go around in the loop here. Up, down, strange, etc. So here we have a negative coupling culture. That means that as a function of, so GR of mu will go down as a function of mu. That's asymptotic freedom. So that's really where it comes from renormalizing the QCD coupling. And it's particular, it's this diagram and this diagram. Now, depending on the gauge choice, you can have different mixtures, but in the end, the result is always this. That's gauge invariant. So I've shown this a little bit through an analogy that the QCD coupling has this opposite behavior in sign to the QED coupling. It's the only type of theory, non-abelian gauge theory, that does that. Now, thankfully also, even though we could have been happy, could have cheered too soon, if we had discovered 18 quark flavors, right? Then yeah, it's negative, but then if you plug in 18 here, you still get a positive number. So thankfully, we've only discovered 6. We're safely in the negative region. This is the first order correction. Could also be that this is negative and that the g to the 5th term is hugely positive. And there's another time that we cheer too soon, but it isn't. In fact, 4 orders have been computed. The 5th is almost finished. The 5th is done actually, and they all enhance. They all leave the negative behavior. So this asymptotic freedom is true up to 5th order in perturbation theory, and I think that's good enough to not to despair that the 7th order suddenly is enormously large and overwhelms all the others. So what is then the solution? We've written down the solution here. A well-known form of the solution for QCD. That's maybe the end of the lecture. So G R squared, and I merely make it divided by 4 pi, which is alpha S of mu, is, and the solution, that's the solution to mu dd mu on G equals this. It's very much the same as what I did there, now done for G, and with the minus sign, and the answer is 4 pi over beta 0 divided by the log of mu squared over lambda QCD squared, where beta 0 is a 11 minus 2 NF, or 33 over 3. And you see here indeed, if lambda gets bigger, if mu gets bigger and bigger and bigger, this gets smaller and smaller and smaller. So indeed it falls off. Now what is lambda? So here we have this is alpha S of mu versus mu. It will go like this, so it will become really small at large scales. That's what we had seen in the Parton model. And here we had seen this Landau pole at enormously large scale. Right? Well, it's a theoretically interesting thing, but completely irrelevant in any practical sense. Here, the Landau pole is on the other side, it's here. precisely where lambda occurs. Indeed, when mu is equal to lambda, infinite. So you can use the lambda pole also in some sense as an initial condition. So that's how renormalization leads to a running of a coupling, a mu dependence of a coupling. We'll discuss tomorrow how to think about that a little bit, what to choose for mu. It's arbitrary, but it's not. You cannot choose mu equal to the mass of this building. I mean, you can, but it would be a stupid choice. You should also not choose at 0. Then you're on the other side of the lambda pole, and know what that means. There are sensible choices to do, and we'll discuss those tomorrow. But this story, the calculation of these diagrams, that led to the Nobel Prize in 2004. This Gross-Wilczek-Politzer. A very important thing, and it allows that even a strong interaction, how can we make any sense these forces hold protons together, and you can never get a free quark, but nevertheless, because of the asymptotic freedom, you can do perturbation theory, and that's why we're here. Okay, that's maybe enough for today. Are there further questions?
Taking into account higher orders affect lambda QCD much?
A little bit. So you have to indeed, when you really are professionally active, you should say calculate in what calculational scheme and to what order. But it hardly changes. Yeah. The typical value is about 200 MeV, which we're quite pleased by because that is also roughly the size of the pion mass. So the low energy QCD scales are similar, the pion mass and lambda QCD. So here you expect that really strong binding effects start occurring, and you should drop perturbation theory. At least quark-gluon perturbation theory, maybe chiral perturbation theory can still work. But you should always use perturbation theory in processes where the typical scales are larger than a few GeV. In that case, this log is large and the coupling is small. And you can do some perturbation theory. Even better if you had hundreds and hundreds of GeV and the coupling is quite small, and you should do much better.
If a lambda q is asked that the inverse of the coupling is 0.
Sorry, at
If a lambda q is asked that the inverse of the coupling.
lambda q is defined by the fact that the coupling is infinite.
I think the inverse of the coupling is 0.
Yes. Yeah.
Asked that.
Yeah, that's right. Yeah. Okay, I hope this was a fairly coherent story. This is not that you need to now know all the steps for this for the future, but it helps to have seen, I think, the logic of renormalization and what it leads to. Okay? Then more in the tutorials and the lecture tomorrow.